All right, section 10.4, we're going to be taking a look at something called polar coordinates. So let me remind you the rectangular coordinates that you've known all the way along. So in the rectangular number system, this is polar still, I'm going to get there, but in the rectangular number system, we call every point by their x and their y location away from the origin, right? How far left and right we went, how far up and down we go. Okay, with polar coordinates, we do something a little differently. This is a system using coordinates based on the distance from the origin. So like as the crow flies, right? So like if you took a string and attached it to 0, 0 and stretched it out, it'd be like the radius of a circle kind of thing. So the distance to the origin, and we call it r. And the angle measure that is from the positive x-axis. So it looks something like this. We have a point out here in space. Normally we would have labeled this x and y, correct? Okay, cool. What we're going to do, and I'll change colors to signify that we are going to identify this now with, we'll do orange. And orange here, is that we're going to figure out how far away from the origin it is, and that length right here is going to be r. And we're going to figure out the angle measure from the positive x-axis, and it's theta. And just like with everything else, our theta is going to be measured in radians. Now, obviously, there's a relationship between the theta, the r, and the x and the y.
So the r
this is trig, right? Go ahead.
R and theta is the polar coordinate.
Yep, the r theta is the polar coordinate that we've referenced up here. X, y is our normal rectangular coordinate that we've been using prior to now. So can you tell me some relationship you see here from what you remember about trig? Some of you were in my office complaining about trig. It's been a minute. Okay, tell me that one, Sophia. You've got one of them. Nope, the first one you said. Tangent. Okay, so if I were to drop a perpendicular down, let me shift this over so it's not running into it. And do that. Try one more time. So if I were to drop a perpendicular down here, like this, then this would be the y distance and this would be the x distance, correct? Okay, so there is a tangent that is being involved. Do you remember what that would be? Tangent of theta is what? It is y over x. You can also think of it as opposite over hypotenuse, right? So the opposite of the angle theta is y, the adjacent is x. So that's one relationship that's in the triangle. There's one more. What is it? X squared plus y squared equals r squared. Pythagorean theorem. Okay. There's two more I'm going to give you, and they relate sine and cosine, which might have been where you were headed, Sophia. There is a relationship of what's happening between the x's and the y's and the theta with sines and cosines as well. So x is equal to r cosine of theta, and y is equal to r sine of theta. And it's just application of SOHCAHTOA, right, in a triangle again. So if we were looking for a relationship for, say, cosine, let's just do the cosine one. I'll do one or the other, but they work the same way. So if I did the cosine of angle theta, the cosine of angle theta would be adjacent, which is x over hypotenuse, which is r. So this would be x over r. And if I solved this for x by multiplying r to the other side, I'd have this equation. Okay? So these are going to be the four conversions that we're going to be able to use, or four equations we're going to be able to use for converting from polar to rectangular or rectangular to polar. And obviously they are nice in different ways, right? So like I can't use the Pythagorean theorem and find my angle. Like that's not useful at all. But I could find x and y very directly with these bottom formulas, but they only work very nicely if I happen to know both the r and the theta, right? So there's pieces that are involved in different ones of them, and they're useful in different ways. And you can use them, if you have the details, in any which way you wish, and you're going to get the same answers, right? Okay, so we're going to take an example. We have the polar coordinate, right? It's given to us, and we're going to graph it. And then we're also going to find the xy ordered pair that it corresponds to. Right, that's the rectangular representation. So to start with, we are going to practice what it looks like graphing in polar. So we start with the first piece. This is the r. Whoops, let's try that again. R says -3. So that sort of seems funny right off the bat, Because how did it describe R over here? I promise I'll come back to it. Oops. How did it describe R?
It is this squared.
No, in the definition.
Oh, in the definition.
It is what? It is the distance from the origin, and now all of a sudden I gave you a negative number. So what's that do? Well, that's okay. It just means it goes the opposite direction. So normally, if we were given a positive value, we would move to the right, just like we would with an x value that's positive. So if we're given a negative, we're going to go to the left. So starting out with x equals -3, r equals -3 means I'm over here. Okay, does that make sense? So I haven't finished where I am, but this right here is where I'm currently located when I went -3 away from as the r value away from the origin. And then it says that my angle measure is 3 pi over 2.
Wait, so why do we go to, like, you're treating R as the X here, but it's usually a diagonal.
Well, it's not a diagonal. We're not there yet. It's just a distance. So if you want to think about it this way, this is where my r value of -3 is currently.
Okay.
But in space, that ends up in the same location as -3 for the x-axis right now. All right, 3 pi over 2. What is 3 pi over 2? Okay, so it's normally on the negative y-axis if I were starting here. But I'm not starting here. I'm starting with my orange circle. So what am I going to do to get 3 pi over 2? Yeah, it's going to go all the way around to here. Are you with me? This is the angle measure that I'm swinging around. It's supposed to be swinging around 3 quadrants worth, essentially, right? I'll show you another way you can graph this too if it helps you. But this is one of the options. So my final resting place, if you will, it sounds like I'm dying, but my final resting place would be right here. This is the polar coordinate that's being described. Now, there's other ways we could describe that point in space with r and theta, right?
The actual
And not even with x's and y's, but with r's and thetas. So let's answer the question that we're asked first, and then let's explore just a little bit of what other r theta values actually land me right here. What is this xy coordinate pair? Because it says it wants us to find its rectangular representation. What is the rectangular representation for that point?
X is going to be equal to -3 cosine.
No, you're overthinking. It is 0. Somebody said it. Not 1. 3. It's 3. It's still 3 away. Okay, it's 0, 3. So x is 0, left and right 0, up 3. This is the point 0, 3, right? Okay, if I didn't just blow your mind by introducing a new coordinate system and I plotted that point, everybody would have been just fine with the fact that this is 0, 3. So you should still be okay with the fact that this is 0, 3. It didn't change. Now, that's not the only way that we could write that polar coordinate. How else could this polar coordinate, and I'll use that orange still because orange is what I was using my polar to be in. How else could this polar coordinate be written?
3.
It could be 3, and then pi over 2. But it could also be 3, 5 pi over 2, couldn't it? And 3, 9 pi over 2? So here's the deal. We've got a unit circle going on, whether you like it or not, Connor. Yeah, we do. And every point in polar is going to have more than one representation. Not only does it have more than one representation because we can spin around and around and around, we can actually start with a negative value at the beginning like this one did instead of a positive value and create a different expression too. Now, let me make one more observation with you about how you could graph these if you didn't like the idea of going at it the way we did. You could start with the angle measure, and that would be okay, all right? So if we go from an angle measure, we would start from the positive x-axis over here, so we'd be starting from over here. And we would go 3 pi over 2. So 3 pi over 2 would put me down here, correct? That's where 3 pi over 2 would do, okay? But I'm supposed to be making the distance from the origin to that location. But the origin to this location, if I came straight down, would be a value of, in our case, is 3. That'd be positive, and ours is negative, so ours is going to go back up instead and land here. So if it helps you to think about doing the angle measure first, and then the direction, kind of like a vector, second, you could do that. Okay? All right, I think we have one we're changing a different way. Yeah, so this one's find the rectangular coordinate for the given polar coordinate. So same kind of direction. We aren't asked to graph this one, so you can if you'd like, but you don't have to. And so this one is not very nice in the sense that it's pi over 4, which means I'm not going to be landing on one of my quadrantal angles, right? I'm not on a positive x or negative xy axis. I'm not on any of the axes when I'm in that zone, so that's not quite as friendly. So in this case, it might actually be easier to remember that we have some formulas that can find x and y for us. X is equal to r cosine of theta, and y is equal to r sine of theta. And we have r and theta. So x is equal to 2 cosine of pi over 4, and y is equal to 2 sine of pi over 4. Now, nobody's making you, as in forcing you to remember what the cosine or sine of pi over 4 is, but your calculator will only give you a decimal approximation, which you at least have to recognize as what the actual value should be. Do you know, we'll do cosine first, what the cosine of pi over 4 is? It's square root 2 over 2. You got it. So the 2's here still at the beginning, and then I have square root 2 over 2. What's the sine value there? It's the same. So if you're thinking unit circle, you're thinking this location right here, right? It's halfway. This is the angle pi over 4 approximately. And this point right here is square root 2 over 2, square root 2. I'm off screen, hang on. Square root 2 over 2. Yep, so then it will cancel the 2's in the denominator on each of them. So the ordered pair is actually square root 2, square root 2, and then we write it as an ordered pair, square root 2, square root 2. Okay, does that make sense? You could also draw this into a triangle, right? I mean, like you see the triangle present in that angle, don't you? Right, just like we drew the triangle on the first slide. Okay. So we had mentioned, and so we will actually do one now, that we can find more than one polar representation for a given rectangular coordinate. We can find infinitely many, in fact, but we're usually asked to find a couple when they ask a question like this. So that's what this one says. Find 2 sets of polar representations of the given rectangular point. Now, I do think, for the most part, drawing pictures are very helpful, so I tend to go to the picture as the first thing, whether I'm told I have to or not. So our ordered pair here is 3, 4, which puts me right here. And the triangle that gets formed looks something like this. And it's actually a very friendly triangle. This one's 3, this one's 4. Do you know what the third side is?
5.
It is 5. That's a Pythagorean triple that is very handy to know. And I want to find the ordered pair in polar coordinates that goes along with this rectangular one. Now, part of this is really easy. What's R?
5.
R is 5. Everybody good with that? Okay. So R is 5. That's not a problem. You could also say that R is negative 5, right? The angle will be a little bit different when we do that. And we need 2 of them anyway. So I'm going to do one of them negative just as a reminder that that's an option. But 5 is sort of the natural one to choose. The angle measures something between 0 and 90 degrees, or 0 and pi over 2, correct? But it's not a unit circle one. So don't go thinking that that is. When the sides are so wonderful, whole number value like this, we don't get nice angles. You get one or the other. So how could I find what that angle is? I can do the tangent of theta. That's the angle measured in the middle. And it's going to be what? Equal to what? 4 over 3. And how do I find theta? Inverse tangent. You got it. Now, make sure you're in radians when you do it. And we'll do a decimal approximation. I have 2 decimal points written down, so we're going to go to, it will hopefully it should tell you the number of decimals at once. So what do you get when you do the inverse tangent of 4/3? It's a decimal. I'll go with that first. What'd you get, Braden?
You said 2 decimal places?
Yep.
1.93.
Okay, 93. So we have the ordered pair 5 and then 0.93. Now, we talked about that with the fact that this is a unit circle. We could just take that angle, which is right here, of 0.93, and we could swing that around 2 pi more, right? So we could get another one just by using this and saying that we're going to do 0.93 plus 2 pi, correct? So we could just do it that way. What do you think we might need to do if I want to use negative We'd have to add pi, exactly. So we'd have our 0.93 and we'd add a pi to it instead. That would take care of it. So we did over and above what we were asked because we found 3 instead of 2. All right. Now you ready to look some graph stuff? Because now we are going to actually graph something that's more exciting than points. Okay, we're going to use a graphing utility, that i.e. calculator. So grab your calculator out. To graph the polar equation, and we're going to find an interval over which it's traced exactly once. So there's a lot of details in there of things that we've not seen before, but did you know that you can graph polar equations in your calculator? So the first thing you need to know is how to change the calculator. So if you have it, please grab it, and I want you to hit the button that says mode. Now, there's lots of options in there. Probably the radian and degree one is one that's pretty familiar to you. And so there's that one. Make sure you're in radian mode. I just have to change mine because I'm teaching a trig class. But right underneath that, at least on my screen, it says function, like F-U-N-C. And then right next to it, it says P-A-R. And then over it says P-O-L. Do you see where it says P-O-L? That's polar. Just choose it. So highlight on top of P-O-L. We will come back to the P-A-R when we get to chapter 10. That's parametric. Okay, are you in polar? Hit y equals. What does your equation now say? R equals instead of y equals, right? Okay, so in order to graph polar, we have to have the equation solved for r. So our first equation that we're given is solved for r. That's great. We can actually put it in just like it is. So we're going to type in 2 minus 2 cosine of theta. And if you hit the x, like where you normally hit x, it actually says theta now. Does yours say theta? Wonderful. Okay, don't go graphing this yet, because right now your window is probably all still messed up, or at least it's not necessarily how we want it to be. So I want you to hit window, and you'll see you have lots of options. You've got options for theta. You've also got options for x min max and x scalar, and then, yeah, that's it. Okay. Oh, no, there it is, y min max. It's like, where's my rest of it? Right, y min and max and the y scalar. Do you see all the choices you have? More choices than before. Okay, so I want you to think about the graph of what we're actually looking at. This is a cosine graph, right? So we know a lot about unit circle. You do know, whether you remember all of it on the spur of the moment or not, you do know a lot about the unit circle. You also know a fair bit about graphs of sines and cosines. Do you remember what the period is for a sine or a cosine graph? How long does it take before it repeats itself?
2 pi.
It's 2 pi, okay? What's the period for a tangent graph? It's pi.
Yeah.
We don't need that, but I just throw it out there. It's not always 2 pi. Okay, so this is 2 pi. So right now my screen says theta min 0, theta max 6.2831853. Does yours say that? Why do you suppose that it might be the default that it's going to do that? Because it's 2 pi. Okay, that doesn't mean that that's what we need. It might repeat quicker or it might repeat less frequently depending on what the angle is that we're working with. Cosine here is just cosine of theta, but if this said cosine of 2 theta or cosine of 1/2 theta, the period changes, and this theta here inside your calculator is going to need to change as well. All right, so 0 to 2 pi is a good first guess as to what this will work out to be. Your x min, x max, y, and then y min, y max, the scalar part being 1 is fine. Why it says x, s, c, l, that's the scalar. That's how often it puts little hash marks everywhere. Usually a 1 there is fine. Negative 10 to 10 is overkill here. What's the amplitude of sines and cosine graphs? 1 and 1, right? They bounce up and down between 1 and 1. So the second part of this graph here, 2 cosine theta, that one's 2, correct? So the idea of it going up and down maybe between 2 and negative 2 seems reasonable. But we've got this extra factor of the 2 in the front. So that's going to affect some things too. If you leave this as negative 10 to 10, in fact, let's just do it. Hit graph and see what happens. It's not terrible, but it's small, right? It's small inside of your calculator. You've already changed yours, Adam. What did you change it to?
5 and 5.
5 and 5 was my suggestion. So take your window and don't mess with the theta. Your x min negative 5, x max 5, y min negative 5, y max 5. And Adam, was it a good window?
It's a pretty solid window.
It's a pretty solid window, I agree. Okay, and you have probably one of the most interesting graphs you've seen on your calculator in some time. Agreed? First of all, you might notice that in terms of the way we've thought about it before, it doesn't look like it's a function. Do you remember what a function is? graphically? It does. It has to pass the vertical line test. This thing does not do that, does it? So in the normal, like screen that we're normally in, you can't graph this picture unless you put it in as two different equations in y1 and y2. So that's kind of a cool feature already. Okay, so we're going to actually graph this thing on the screen. You could make your window a little bit shorter on the positive x side if you felt like that it would help you to sort of see a little bit better picture of what's going on. I don't think we need to, so I'm not going to. But the graph looks something like this. Now, in terms of what do I need to make sure is on my features when I sort of draw it, you should be hitting the axes in the right locations and trying to get the general shape in the same, okay? So we've all agreed, at least, that I'm not an artist. I don't know. Did we decide if any of you guys are? Is it a no? Is everybody a no on that one? Yeah. Okay. So this one is hitting over here at -4, correct? And it hits at the origin as well. That part I think is pretty clear. And then it looks like it's hitting at 2 and -2, or at least really close to them on the y-axis, correct? Right? So we're at least going to be awfully close to those values, so I'm going to put those in. Plotting some points individually will at least help you to get the image to look right. The graph looks something like this. It looks a little more circular than mine. Let me try that again. Okay, I think that's pretty all right. Does yours look pretty close to that? Connor's like, no, of course it doesn't. Okay, this has a name. This graph has a name. I'm not going to ask you to remember the names, but I want you to know that it does. It's a cardioid. And the names, I've got this stat written down. I think it's still correct. Even, hell, it might not be because we've changed editions. But the names are located in 10.4. We'll say that. There's a whole bunch of names for different graphs. This one's going to be in 10.4. My page number is probably not 725 anymore, but it's close to there. There was something else it asked us to do besides graph. What was the other part of the directions here? To find the interval, right? So we think that this is enough, right? Because if we repeat the theta values, it should just be repeating the same thing around the circle again, because that's the period for cosine. Like, that seems reasonable. And so if we're correct, then this will actually be enough. So our theta is going between 0 and 2 pi. I'd like for you to see what your calculator does if you put something in that's too small or too big, just so you can see what will happen, okay? So go ahead and hit your window button. Let's let your theta max just go to pi, all right? So just change it, say, from 0 minimum to pi, and graph. And what happened?
Half of it.
You got half of it. You got the top half. Now, we know that's not the complete graph because we've seen the complete graph. But if you got this graph, you should also know that it's not complete because it didn't start and stop in the same place. Are you with me? So if you started out being really sure that this thing was only from 0 to pi and you got this graph should tell you that you're incorrect. Now I'd like for you to see what happens if you go too far. So let's hit your...
How do you tell it tells it's incorrect?
What's that?
How do you tell it?
Because the ending is not back at the beginning.
Okay.
It should end and start at the same place. Okay? Hit your window, and I want you to make the window go too big. So let's just go to 4 pi. You could do 3 pi if you want, that's fine too. But you need to watch carefully while the graph graphs, or you're gonna lose all effect, okay? So watch what happens as the graph graphs it, because it's still gonna give you the same picture we had first. Did you see what happened anywhere on the screen that told you that it was going back over itself? Okay, I want you to hit y equals, or not y equals, hit mode. That's still not the button I want. Window is still the button I want. Hit window. Type in again 3 pi or 4 pi right on top of what you did. And I want you to look in the top right-hand corner after it finishes graphing what you think to be the whole graph. Are you asking, you hear what I'm saying? So if you hit graph now, it's going to graph this graph, and in the top right, well, you've got to change something. I'm sorry. hit something else inside of R1, type over one of those 2's or something and hit graph. Otherwise, it just doesn't know what to do. But in the top right-hand corner, there's a scroll bar. Do you see your little scroll bar going on in that top right-hand corner? It's kind of like the spinning wheel of death on your computer, you know, when it's like trying to find something for you and you're like, would you just find the thing? This scroll bar tells you it's still graphing, but you don't see it doing anything else. Are you with me? I want to show you one more cool feature that you need to be aware of in case it should happen to you. You saw theta min, theta max. Change it back to 2 pi because we know that's right. We didn't mess with the one that said theta step, did we? We didn't do that. The theta step that it gave us was pretty good. What I want you to do is I want you to make that theta step value, which mine right now says 0.13089. Did you say that? Okay.
Yep.
Okay, so I would like for you to change it to be something not helpful. I'm not sure how big I have to do to make it not helpful, so let me play with it real quick just a second. No, that's probably not big enough. Try your theta step to be 0.4. Yeah, that's pretty good. If you make your theta step 0.4, what happened on your picture?
It's fast.
It's fast. It graphed fast. That's one thing.
It's also choppy.
It's choppy. So this is like what happens, you know, when the children get the connect the dots puzzles, you know, like at the restaurant, and they're connecting the dots, but they don't connect the dots smoothly. Is, you know, anything that has a curve looks funny because it's got a jagged edge. What your calculator is doing is it's plotting these individual points and it's connecting them. And if it doesn't plot enough points and connect them, it looks jagged. Now, is it jagged? Well, no, it shouldn't be, but it's because your calculator is using numerical approximation to do this, right? We saw this happen in Calc 2 and Calc 1 at different points when it would find some sort of a numerical approximation that you knew the derivative was supposed to be 1, but it told you it was 0.9999986, right? And you're like, no, it's 1. I know it's 1 because your calculator's not doing calculus. It's doing numerical approximation, right? Same thing's happening here. This is numerical approximation, and then it's connecting it just like the child at Chili's does with the Connect the Dots menu, okay? So, things to be aware of. Please change your your window back to having that t-step at about 0.13. Oops. And if you graph it, it'll be nice and smooth again. Okay, all good?
Yep.
Okay, let's take a look at another one. I think we did everything it asked us for here, so we're good. This one wants to sketch the graph of the polar coordinate and to find the corresponding rectangular equation. Okay, corresponding rectangular equation. So we're going to graph it with calculator. Okay, so we're going to clear out our R1. We're going to put in 2 sine of theta. We expect that it should be the theta going from 0 to 2 pi, but we want to watch the screen, especially in that top right-hand corner, to see that it really works, right? Oops.
Interesting.
Oh, I typed cosine. I was like, that's not what I was expecting. Let's try it again. Okay, what does it look like? Adrian, you started to tell me.
It's an oval.
It looks like an oval.
Oval.
Is it really an oval? No clue. Did it go over itself? I told you to watch and then I didn't do it. Did it type over itself?
Yeah.
I thought it did. Okay, so the theta went too far this time, correct? Our theta does not need to go from 0 to 2 pi. It actually only needs to do what? Pi is enough. So if you can change your mode, that will look, not your mode, your window, that'll be good to only go to pi and graph. And Adrian pointed out, and he is right, your screen right now, it looks like it's an oval. My question to you is it really an oval?
No.
It's not really an oval. Do you know why your screen makes it look like one?
Because your screen is wider than the top.
Yes, your screen is not square. You've got a rectangular screen, correct? So the problem is that your -5 to 5, which is what we still have ours at, is wider in -5 than it is a tall -5 because we've got a rectangular screen. This really isn't an oval up there. It's a circle. Okay. Circle of radius what? Can you tell? I believe it's a circle of radius 1 as well. Okay, so we've got a graph. It's actually a circle. It's of radius 1. Where is its center? Its center is at 1. So we have a graph that's actually, let me move this up some. There's the center. And it's like this. It's coming out here to -1, and it's coming over here to +1. And my theta is going actually only this time between 0 and pi, even though we thought it might be 2 pi. This is our graph. This is our equation that we're supposed to graph. It also asks us, though, to turn this into a corresponding rectangular equation. Well, right now I've got r equals 2 sine of theta. I need to change this so there's no r's and there's no thetas in here, but instead we have x's and y's. There's more than one way to do that here. Any ideas about what you might try? We had 4 equations. Actually, let me copy them and put on the screen so that we have them here. These 4 equations are the ones we're going to think about. That's not what I meant to do. Try it again. Here we go. Here, we'll put them down here. What might we try and do from this list of options to eliminate the theta and the r?
You could do 1 equals 2 sine theta.
1 equals 2 sine theta.
Find the angle.
Okay, so you would like to find the angle, perhaps, to start with, or at least an expression for the angle, correct? Because we don't have an actual angle because that's a variable quantity here. So tell me again what you just said, Ben.
1 equals 2 sine theta.
Okay, so can we, because r is 1 in our equation here, I see. So this would be one way to start. It's probably not the most direct way. Instead, let's actually talk about that angle that you mentioned, though, and let's rewrite it in terms of sine of theta. What would sine of theta be written in terms of this equation? R over 2. So do you see an expression down here that tells us a way to eliminate sine of theta? Yeah? Y is equal to r sine of theta. Now, we don't have r sine of theta. We just have sine of theta by itself. But could I manipulate this so that it just says sine of theta equals something? What would it be? Y over r. So I actually have this equation. Let me use a different color down here. And I can rewrite this as the sine of theta is y over r. So I can take this equation. Here's where we are at this point. I should have just written it underneath there. And I can replace sine of theta with y over r equals r over 2. And I no longer have a theta involved. I do still have an r involved. Okay, this isn't the only way to do it. It's not even how I've done it on my paper. What could I do next? Oh, you could cross multiply, sure. So 2y equals r squared. Now what? We don't want to. Our goal is to get rid of the variable. What? R. We'd like to get rid of the variable r. But do you see a nice formula that could do that? Anybody? The Pythagorean theorem one, you bet. Do you see that one that says what r squared is right here? R squared is x squared plus y squared. So I can keep the 2y there. I can replace this as x squared plus y squared. And I've actually done what they asked me to do, right? Which was to rewrite this in rectangular form. Now, it's not a form that we normally write this kind of a image in. So I'm going to manipulate it a little bit just so that you can see that it really is a circle. That's what I want to do real quick. I'm going to move the 2y to the other side. So x squared plus y squared plus 2 minus 2y. I'm going to do something you're not going to like. It's called completing the square. So the middle term, -2 divided by 2 squared is 1. If I add 1 to the right, I have to add 1 to the left. I did that so that this will be able to be factored perfectly, which it can be as y minus 1 squared. And then do you see the center of the circle at x is 0, y is 1? And do you see the radius is 1? Yes, we do. So we end up with this circle in the standard form and can recognize that.
In the test, you want us to put in standard form, or you need y equals x squared?
So it's going to want you to put into standard form. We're going to do more with the standard forms of things later, but yeah. All right, so here's the deal. I don't have time for my last two examples. I think I do have time for example 7. So I will post my video from last year ago so you guys can see example 6 because it's a little more involved. But let me do example 7 real quick because it's really fast, okay? It's the same manipulations of things that we just did, converting into rectangular form. It's got the sketch, the graph. Your calculator will do that, but you'll also recognize the equation. The cosine of theta is x over r, much like we did the sine of theta just a moment ago. And if I multiply the other side, I have r squared equals 4x. And then r squared is x squared plus y squared. And I can manipulate this the way that I did on the other screen with completing the square. I have a positive 4 here and a positive 4 here. And it factors as x minus 2 squared plus y squared equals 4 squared. Or, well, 2 squared, which is 4. So it's another circle. Right, it shows up as another circle. Its center is 2, 0, and its radius is 2. So you can graph that either from the calculator's perspective and the rectangular or the polar equation you originally given, or from your knowledge about conics is what this is, which is what we'll study more about in depth in chapter 10. Because I can see the radius. The radius is 2 if I write it as 2 squared. That's the only reason I did that. You can leave it as 4, but it is a radius of 2. And the center is 2, 0.
Oh, because that
Yeah,
shows you the
I was just showing
diameter.
the diameter. Yeah, the radius for the diameter. Okay, I will stop this video. I will post my video from last time. You can just zoom forward. I'll even tell you where to start the video, and it'll have example 6 in it. Okay?